Hello everyone. Hello everyone. I am Soumojit Chatterjee and this is TLE Eliminators. Welcome to the post-contest discussion of today's CodeChef contest. We will discuss the solution of the first 4 problems today. So I hope you all had a great contest. So before we begin, let me just confirm whether my voice is audible and my screen is visible or not. Guys, can you all give a quick confirmation in the chat? Okay, great. So let us begin with the first problem. So this is the first problem. It says GCD summation. So the question says that for an array A of length n, we define f of A. Okay, give me a minute. Okay. So the question says that for an array A of length n, we define f of A to be the sum of GCDs of its adjacent elements. That is, f of A is the sum of these n minus 1 terms, where we take the GCD of AI and AI plus 1, that is 2 adjacent elements, and add it up. We are given two integers n and k, and we need to find any array of length n consisting of all distinct integers between 1 and 10 to the power 9, such that f of A is equal to k. If multiple valid arrays exist, we may find any of them, and if no valid arrays exist, we print -1 instead. Okay, great. So let us start discussing this problem. So the question says that we are given two integers as input, n and k. Okay. And the question defines f of A for some array A to be the sum of adjacent GCDs. So it says that for a zero indexed array A, you just go from I equal to 0 till n minus 1, and you take the GCD of the values AI and AI plus 1. For the sake of concreteness, so suppose I have been given an array 1, 3, 6 and 2. Suppose this is array A. Then the value of f of A will be the GCD of 1 and 3, which is 1, the GCD of 3 and 6, which is 3, and the GCD of 6 and 2, which is 2. So this is equal to 6. So this is how an array A and the value f of A is defined. Now, the question says that we are given these two integers n and k, and we need to print an array A of length n. So we need to print an array A which is of length n, such that the value of f of A is equal to k. And we need this to be exact. So we need to print some array A such that the value of f of A is exactly k. So let us see how can we do that. Now, the first thing which comes to my mind when I read this problem is that, okay, what is f of A? F of A is basically sum of n minus 1 terms, right? So it is nothing but sum of n minus 1 GCDs. Great. Now, if you think about one GCD, the value of any GCD should be greater than equal to 1, right? So you pick any two numbers and find out their GCD. Their GCD should be at least 1. And what is f of A? F of A is the sum of n minus 1 such GCDs. So that means f of A for an array of length n should be at least n minus 1, because it is the sum of n minus 1 terms and each term should be at least 1. So f of A should be at least n minus 1. And our target is to make f of A equal to k, right? So this gives us to an implication that k should be at least n minus 1. So the first thing which we get is that if we see that the value of k is less than n minus 1, then we simply print a minus 1. That is what is stated in the question. If we read the question once again, it says that if no valid arrays exist, we print minus 1. So that is the reason whenever I see that, okay, the value of k is less than n minus 1, it is not possible because the sum of n minus 1 terms would be at least n minus 1 and k cannot be matched with that. So we simply print minus 1 in this case. So for all other cases, we can now safely assume that k is greater than equal to n minus 1. Because if k is less than n minus 1, we have already printed minus 1 and have terminated the program. Great. Now what happens if k is greater than equal to n minus 1? Now think about it. How will you write f of a? F of a is basically sum of GCDs, right? So think about these. There are as if there are n minus 1 GCDs. And I want to make their total sum equal to k. Now my target is to make all these terms equal to 1. My target is, why not, I have to finally make the sum equal to k, right? So why not make all these remaining terms equal to 1 and make this term equal to k minus n minus 2. If I do that, so the value of g1 would be k minus n minus 2, and then there are n minus 2 ones here. So the total sum will become equal to k. So if I'm ever successful to set the array values in such a way so that the GCD of the first two terms is k minus n minus 2 and the GCD of the remaining terms is 1, then I'm done, right? So this is our target. For simplicity, for the later part of the explanation, let me call this value as r. So r is equal to k minus n minus 2. Great. Now let us try assigning values to the array A. So the array A, it is basically, there are n values. And now what is my target? My target is that the GCD of the first, these two terms should be r. And for all the remaining terms, for any two adjacent terms you pick, the GCD should be 1. That is my target. Great. There is one more condition which is given in the problem, which is that we need to find an array of length n which consists of all distinct integers. So this is something we should keep in mind, that all numbers which we print in the array A itself should be pairwise distinct. We cannot print duplicate elements in the array A. Great. Now, since I need to keep the GCD of first two terms r, what is the obvious choice of setting A1 and A2? Why not simply set A1 to be equal to r and A2 to be equal to 2r? If I do this, the GCD of r and 2r is definitely r. So we are done, right? So setting the GCD of the first pair to be equal to r is simple. Now what remains? I need to set the remaining values in such a way, that all other GCDs which we get are simply 1. That means we need to find lots of co-prime pairs, right? So how can we do that? The simple idea whenever it comes in mind that we need to find co-prime pairs, that is, I need to find AI and AJ such that they are co-prime, their GCD is 1, is to simply take prime numbers, right? So the idea is, why not fill the remaining array with prime numbers itself? So why not? So suppose I have the set of list of prime numbers listed, and suppose it is 2, 3, 5, 7, and it goes on. Why not fill the remaining numbers with simply these primes? If I do that, that ensures that all these possible, the GCD of any two primes, that would be definitely 1, right? So that would not create any concern and we will be done. The only thing which we need to care about is that none of these primes should coincide with 2, and the GCD of 2r and this prime should be equal to 1, right? So my idea is that okay, using the list of primes will help, but then there are a bunch of conditions which I need to take care of. So my idea is simple. Why not first enumerate the list of primes? So my idea is simple. So here is how the algorithm goes. Now let me summarize the entire algorithm once. So if n is less than k minus 1, what did we do? We simply print a minus 1. So that is done. If n is greater than equal to k minus 1, so we set r as, okay, just a second, I did a mistake here, I guess. This should be, if k is less than n minus 1, we print minus 1. Otherwise, we set r as k minus n minus 2, right? And my idea is that, okay, first enumerate the list of all primes. So suppose p1, p2, p3. Suppose this is the list of all primes, right? Now, let me create the array A. Let me keep the first value as r and the second value as 2r. Okay. And for these remaining values, I will just run a loop and keep on putting these values p1, p2, p3, as so on, until the length of this array becomes n. While doing this, I will ensure a few things. Whenever I will put a prime, so whenever I'm suppose in the ith iteration I'm putting some pi value into this array, I will just check that okay, pi should not be equal to r, because if pi is r, then we are not getting distinct elements. Simply pi should not be equal to 2r as well, right? Because that would also create problem because we need distinct elements. And the GCD of pi with the last value which I have set in the array, so say ai minus 1, that should be equal to 1, right? Ai minus 1 is the value which I have last set in the array, so that should be equal to, the GCD of pi with that should be equal to 1. So this condition basically checks that the GCD of the first prime which we keep with 2r, that is 1 basically. That condition is checked in this condition itself. For all other conditions, this will become trivially true because the GCD of any two primes will be simply 1. Okay. Okay, great. A lot of you suggested that the consecutive numbers will also give GCD 1. So I think you all are right. So we could have set the array like this, r, 2r, and then we could have kept 2r plus 1, 2r plus 2. Okay, so this ensures that the GCD of the first two terms is r and the GCD of any other two terms is 1 because they are co-prime. Okay, great. And this also ensures that all the terms in the sequence are distinct. Okay, so this is a valid solution and this is probably a solution much simpler than what I have discussed. So thank you for everyone who suggested this solution. It was really nice. So we got a pair of solutions with us. So this was the first solution. We simply set r, 2r, 2r plus 1 and all consecutive numbers. Otherwise, we can simply append the list of primes into the list, ensuring that the GCD of that none of the prime has a GCD not equal to 1 with its previous element. Okay, great. So both the solutions work. So let me show you the code once. Okay, so this is the code which I have implemented. There may be, as we discussed, there are other solutions which are much simpler, and you can easily code it up. So the idea is same, that if k is less than n minus 1, you simply print a minus 1. Otherwise, you set r, or which I have called rem in my code as k minus n minus 2. You set the first element as R and the second element as 2R. And here what I've done is I've appended the array with primes. While appending the array with this prime, I have ensured that the GCD of the prime with the last element should not be should not, if it is not equal to 1, or if the prime matches with rem, then I just continue and skip that prime and go to the next prime in the list, and I simply append the list with primes. What you could do instead, or that would be a simple solution, would be appending it with just consecutive numbers, and that would work fine. Okay, great. So that was all for the first question. So I hope there's no more doubt and we can continue with the next one. So this was the second problem of the contest, and it says, and the problem's name is Creature Hunter. So the question says that Chef is playing his favorite video game, Creature Hunter, and he is now preparing to fight a difficult boss. The boss has H health, and Chef has N different weapons available to him. The ith weapon takes SI seconds to charge up and then does DI damage to the boss. That is, its health decreases by DI. Okay, great. And the boss is considered to be defeated when its health becomes less than equal to 0. Fine. Now, Chef can repeatedly do the following. Choose any weapon available to him and attack the boss using it. If the ith weapon is chosen, so this will do DI damage to the boss and it will use SI seconds. Okay, great. And Chef can use the same weapon several times consecutively if he wishes to, or switch weapons as many times as he wishes to, and the only constraint is that only one weapon can be used at a time. Now the question asks, what is the minimum time needed for Chef to defeat the boss if he makes his choices optimally? Okay. Okay, so Sam asks a question related to the previous problem. So okay, so I think the problem which may come in the code which you have shared is basically it may happen that the value of val is not equal to 2 times first GCD, but still they are not co-prime. So they may have a GCD not equal to 1, yet they are not equal, right? So this is same as saying suppose first GCD is 2. So first GCD into 2 is 4. Sorry, I gave a wrong example. So think about it like that. What if first GCD is 3? So first GCD into 2 is 6, but then the value of your val is 2. So val is neither equal to first GCD or 2 times first GCD, but it's yet an invalid answer. Okay, so let us begin with the next problem. So the second question says that we basically have lots of weapons. So we basically need to kill a person with whose health is H, and we have lots of weapons which take time either 1 or 2 seconds. So it has some time which it takes, and it has some power, so it makes some damage. So it makes a damage of D. So basically you are given lots of weapons which take SI seconds to give a damage of DI, and it has been said that SI is either 1 or 2. Okay, great. Now, so this problem, now we need to kill this monster in the minimum number of attacks as possible, right? So at first glance, this really looks like a very simple problem, because what we need to essentially do is we need to give maximum amount of attack which is possible to this person, right, in minimum number of time. So the idea is very similar to what happens in, say, a fractional knapsack problem. You basically look at, okay, which weapon should I give, should I attack to for this person, which gives me maximum maximum damage per second. So suppose you have 2 weapons, suppose which one takes 1 second and it provides a damage of 8, otherwise takes 2 seconds and it provides a damage of 20. Okay, so what is important is what is the rate. So what is the rate of damage? So if you think about the rate of damage, so the first weapon gives a damage of 8 per second, right? And the second weapon gives you a damage of 10 per second. So at first glance, obviously the second weapon is better than the first weapon, right? So you will always try to hit this person with the second weapon itself. So there are few observations which we make. So this is the first observation. The first observation is that if there are multiple weapons, so suppose there are multiple weapons. So suppose there are multiple weapons with the same SI value, same SI. So that is basically, suppose you have three weapons, all take 1 seconds, and one gives you a damage of 8, one gives you a damage of 10, and one gives you a damage of 4. Okay, so if there are multiple weapons with the same SI, so you simply throw away those weapons which give you lower damage, right? Because why will you use a weapon which gives a damage of 8 and 4 when you already have a weapon which gives you a damage of 10, that is higher damage in the same time? So you basically simply throw away these weapons. Similarly, if you have, so basically what you remain or what you have finally is two weapons, right? At most two weapons. One weapon which has a time of 1 second and it gives you say a damage of D1, and one weapon which takes 2 seconds and gives you a damage of D2. Right? These are the only two weapons which you have, because other weapons in the same time they were giving attack less than damage less than D1 or less than D2. So you simply throw them away. Fine. So you are left with only two weapons. Great. Okay. So there are only two weapons which we need to consider. So the first weapon, as we discussed, takes 1 second and gives a damage of D1. The second weapon takes 2 seconds and gives a damage of D2. Fine. Now I need to kill a person. I need to kill a person with health H. So what are the choices I have? The first choice is kill him entirely. Kill him entirely with this first weapon, right? So if I kill this guy entirely with the first weapon, how many days will it take? It will take H by D1 number of days. The seal value to be exact. Right. So I'm basically incurring D1 damage every day. So it takes H by D1, the seal value, to kill the person H with health H. The second option which I can do is I kill him entirely with the second weapon. So I take this weapon and use this weapon only to kill him. So I do not use any mixture. Right. So this is the second thing which I can do. So if I do that, it will take H by D2. So this is the number of damages which it will take to kill him. But then we have to multiply it with 2, because for every damage it takes 2 seconds to give the same attack. So if I do it using the first weapon, that is the time I take. If I do it using the second weapon, this is the time I take. Okay, fine. So thinking naively, you would think that, okay, I will take the minimum of these two. I will take the minimum of, there are two weapons. I take attack with both of them. I see what is the minimum number of days it takes to attack using either one of them, and that would be my answer. But this would give wrong answer for one case. Think about a problem. So think about a problem where you have two weapons. One weapon takes 1 second but gives you a damage of 8. The second one takes 2 seconds and gives you a damage of 20. Fine. Now, suppose there is one person who has a health of say 88. Okay. So now think about it. If you try to kill him using the first weapon itself, it takes 11 days, right? Simply edge by d1, so it takes 11 days. And if you try to kill him using the second weapon itself, how many days it takes? 88 by 20, the seal value of it is 5 into 2, so it takes 10 days, right? So you would report your answer as 10 according to our previous logic. But think about this. What if we do like this? We keep on attacking this guy till for 4 times. So basically it took 8 days and we attacked him 4 times. So his health reduced from 88 to 8. And in the next day itself, we used this weapon. So it would take an 8 plus 1, 9 days to kill this person, right? So the basic idea is sometimes it may happen that that suppose the second weapon is more effective. So you are using the second weapon in itself, but at the last day you do not need to wait for 2 more days to provide him the attack, because it may happen that in one more day, using the less effective one weapon, you can simply kill him, right? Here, after 8 days, if I go by this way, after 8 days the damage here itself is 8. But what I'm doing is I'm waiting for 2 more days for this weapon to get charged up, and then I'm using it. Okay, but now here I have a better choice. I do it for similarly using those 8 days, but finally I wait for it, and I check that okay, can I kill him using this lower effective weapon? If I can do this, why not simply kill him in one day itself and not wait for two more days? So this is the reason there are three ways to kill a person which we need to consider. One is simply using the first weapon, one is simply using the second weapon, and the last one is you use your second weapon continuously until so that at the last day you can use the first weapon and kill him. Okay, so I think it would be a bit more clear if I show you all the code. So this is how the code looks like. Look what I've done. First of all, okay, so I've created this array of damage. So it is an array of size 2. So basically just two elements in the array. So it basically D0 stores like what is the maximum damage like a weapon with duration 1 provides, and D1 stores what is the maximum damage a weapon with duration 2 provides. So this is basically like throwing away all the weapons which are of lower damage. Fine. Now look what I've done. So if D0 is greater than 0, that means at least there is one weapon which has duration 1. Then I can simply kill him with the first weapon itself. So I'm initializing the answer with minimum of everything. Okay. So these are the first two cases which we already discussed. Like this is nothing but the seal value of h by d0, and this is nothing but 2 times the seal value of h by d1. Okay. These two are clear. Now look at this third case. What I can do is that I first find out what is the number of attacks which I can make using the second weapon, so that he is not completely killed. Okay, so this is I get h by d1. So this is something like that. Okay, if you think about it, so I had 88, right? So I had this damage of 88, and I used it for 4 days. So instead of completely killing this guy with the 2, using 4 days, this person is not completely killed, right? So I use it for 4 days, but I see that okay, the value of attacks into d1 is less than h. So that means this person is not completely killed if I use these many attacks. But then if I use one more attack of the first weapon, then this guy gets killed because the total damage exceeds h. In that case, I know that 2 into attacks plus 1 is also a valid answer. So I can take the minimum of all these three and finally print out the answer. So I hope it's clear. Any doubts on this? Okay, so if it's clear, let's move on to the next problem. So this is the third question of the contest. It says array deletion game. So the question says that Alice and Bob are playing a game with an array A of length 2n, and the game consists of n rounds. In each round, Alice chooses any element from the current array, adds its value to her score, and removes it from the array. Bob then removes the leftmost element of the remaining array without affecting any score. And this continues until the array is empty. Determine the maximum score that Alice can achieve by playing optimally. Okay. So the question is as follows. It says that you have an array of length 2n. Okay. So let me show it using an example. So suppose this is an array of length 6. Now there are two players, Alice and Bob, which will be playing the game. Okay, fine. Now suppose Alice starts the game. In one move, what does Alice do? Alice picks a value and adds it to his score. So Alice can pick any value. Suppose Alice picks this 9 and adds up to his score. So Alice's score becomes 9. Fine. Now Bob will come and he will remove the leftmost element which he sees. So okay, like Alice, after he selects this option, he will also remove this element. And Bob comes, he sees the leftmost element in the array and simply removes it. Fine. Now Alice can again pick any one of the remaining elements. So suppose Alice picks this 7 and removes it. Okay, so what does the new score of Alice becomes? It becomes 9 plus 7. Now again Bob comes and removes the leftmost element he finds. Okay, so this is important to remember that just like Alice has a choice, he can choose any one of the elements, but Bob does not have a choice. Bob simply comes, looks the leftmost element which is present in the array and removes it. Fine. Now Alice, suppose Alice comes this, takes this 3, removes it from the array. And Bob comes and finally removes this element from the array. Okay, so what does the final score of Alice become? It becomes 9 plus 7 plus 3, which is 19. Now, it has been said that how should Alice play the game? So, how should Alice play the game so that Alice's score is maximized? Okay, Alice needs to so Alice needs to devise a strategy so that he can maximize the score given out of the entire array. Fine. Now there is one important thing to note that okay, there are 2 elements in the array, right? And for every element which Alice picks, Bob comes and removes one more extra element. So that means out of the 2n points, Alice will pick n elements and Bob will pick n elements. That is clear. So Alice cannot pick more than n elements. The maximum number of elements Alice can pick is simply n. Okay, fine. Now, let's try thinking about the solution using some cases. What if the array looks something like this? You have a couple, and then, okay, suppose this is how the array looks like. If this is how the array looks like, how should Alice optimally play? Alice knows that okay, there are 4 elements. There are two elements which Bob will pick. Fine. Now, since Alice needs to maximize his score, Alice should greedily try to pick the first 2 elements, right? Because they're very large, 100 and 101 compared to other elements 1 and 1. But can Alice pick these first 2 elements? Like suppose Alice starts and picks this 100. Okay, so Alice adds up this 100 to his score. But whenever he just the point he adds 100, Bob comes and cancels this 101. Similarly, if Alice comes and picks this 101, Bob will come in his first step and cancel this 100. So that means even though there are out of the first 2 elements, Alice can never pick more than 1 element. Because Alice can never come and pick both the elements, because whenever Alice picks one element, out of the first two elements, Bob comes and picks the other element. So this is the claim which I will try to prove. So let me state the claim first. That out of the first 2i elements, out of first 2i elements, Alice can pick only I of them. Alice can pick at most I of them. Right? We have already checked this statement for I equal to 1, right? Because out of the first two elements, we have already seen that Alice can pick at most one element. Alice cannot pick both the elements. Because the idea is simple. Like, let me try to prove this. So we have already seen that in the first two elements A1 and A2, Alice will not pick, like Alice cannot pick both these elements, right? So this statement is valid for I equal to 1. Okay, this statement is valid for I equal to 1. Great. Now, try to extend this same idea when there are much more elements. So what happens if there are 4 elements? And this should give an intuition of the statement. So suppose there are 4 elements. Now, can Alice pick more than 2 elements out of this 4 element? Suppose Alice picks this A2. So what does Bob do? Bob comes and cancels this A1. Now suppose Alice picks out of one out of these A3 or A4. Suppose Alice picks this A3. Bob would come and cancel this A4, right? So basically, since Bob is starting from the leftmost position and cancelling elements one by one, that means out of the first 2i elements, Bob will definitely cancel. At least. Bob will definitely cancel at least I elements. Okay, so since Bob cancels at least I elements from the first 2i elements, that means Alice can pick at most I elements from the first 2i elements. So my idea is that so what we need to do is to find the solution. We need to, out of this entire array of length 2n, we need to find a bunch of n elements such that this condition that out of the first 2i elements we pick only at most I elements holds for every prefix I. Okay, so suppose I have been given some array A. Suppose I have given this array A 1, 4, 2, 8, 10 and 12. And suppose I need to pick 3 elements, right? So think about this, that 8, 10 and 12. If I try to pick 8, 10 and 12, that would be a valid configuration. Why? Because consider all these prefix. Out in this entire first prefix, I need to pick at most one element. In this entire prefix, I can take at most 2 elements. And in this entire prefix, I can take at most 3 elements. This is my condition. So look that if I take these last 3 elements, then the condition holds for all the prefixes. So I can take this last 3 elements. That means the score of 8 plus 10 plus 12 is achievable. Okay, but now suppose what happens if Alice says no, I will pick the first element, the third element and the fourth element. So is that an achievable configuration? No, because if you do that, you violate the condition for this prefix. Because in this prefix of length 4, you are picking 3 elements, which is not possible. Because Bob will come and since he's alternately cancelling elements out of this prefix, he will come and cancel at least I elements. So out of the 4 elements, 2 elements Bob will definitely cancel. So Alice cannot pick 3 elements out of this first prefix. Okay. So finally what we need to do is that out of this array of length 2n, so now the final objective is that given A of length 2n, we need to find n elements. So we need to find n elements such that the sum is maximum. So there are two things which I need to ensure. First, that the sum is maximum. And the second thing is that for every prefix of length 2i, for every prefix of length 2i of length 2i, we take at most I elements. We take at most I elements. So these are the two conditions which we will try to satisfy. Okay, fine. Now, in order to do this, I will show you a simple iterative solution. So what is the solution? So let me try to show the solution using an example. So let me take an example test case. Suppose this is something like this. We get a 10 and then a 20, then a 7, then a 8, then a 40, and then a fine. So this is the array which we will be dealing with. Great. Now, what I will try to do is I will try to maintain a bag of numbers. Okay, I will try to maintain a bag of numbers. What will the bag contain? We will run from each I, from I equal to 2, 4, 6, 8 and so on. And then we will try to maintain that, okay, out of the first 2i elements, which are the best I elements which I can keep in the bag. Okay, so this is the bag which basically Alice will try to pick. So finally, we will have a bag of n elements and its sum will be the answer. Okay, fine. So let us start from the beginning. First, for the first I equal to 2 elements. So here we are ensuring the first. This is the first iteration up to I equal to 2. Okay. Up to I equal to 2, we know that there can be only at most one element in the bag. So out of 10 and 20, which is the maximum? 20. So let me keep 20 in the bag. Okay, so the bag contains only one element, which is 20 out of the first 2 elements. Fine. Now comes the next 2 elements. Okay, so I will extend this iteration till I equal to 4. Now, how should I update the bag? Now, the idea is, how should I update the bag so that the bag contains 2 elements and the condition holds for both the prefixes? Okay, so my idea is simple, that okay, for up to this part, my bag is already constructed. I can get I have 2 more extra elements, right? So why not pick both of these in the bag? Okay, so now my bag contains 3 elements. What are the elements? 27 and 8. Okay, so there are 3 elements in the bag. But up to I equal to 4, I cannot have 3 elements in the bag, right? I can have at most 2 elements because that is what Alice can pick maximum. So I have to remove one element from the bag. So which element should I remove? Let us remove the minimum element. Because if I remove the minimum element, that will ensure that the score is maximum. So I remove 7 from the bag. So now the bag contains 2 elements, 20 and 8. Fine. Now let us continue again. We are iterating till I equal to 6. If I iterate till I equal to 6, I get 2 more extra elements, 40 and 60. What do? The first thing is you add both of them in the bag. Okay, you add both of them in the bag. So how does the new bag look like? If you add both of them in the bag, the new bag looks like 20, 8, 40. This bag contains one extra element because out of these 6 elements, you have 4 elements. So remove the smallest element from the bag. Okay. If you do this, you finally ensure that your bag is of size n and it considers a valid configuration. It basically satisfies the condition for all the prefixes. So basically 20, 40 and 60 is the maximum score Alice can get. So the idea is, so this is something like of an inductive approach, that I know that if up to index I minus 1 my bag is computed. So suppose this is the index I minus 1 and I have these two values ai and ai plus 1 sitting here. Okay. And suppose my bag is computed up to this index I minus 1. So up to this index I minus 1 I have this bag which is computed correctly. How many elements? Extremely sorry. So it contains, just a second. Let me write it like this. So this index is up to 2i minus 1 and this is 8 2i. Okay, just a second. So suppose this index is up to 2i and these are the indices 8 2i plus 1 and suppose this is the index 2i plus 2. Okay. And the size of this bag is the size of index I. So the size of this bag is I. Okay. Now I need to include these two elements 8 2i plus 1 and 8 2i plus 1 and 8 2i plus 2 so that finally the bag contains I plus 1 elements. So what do I do? First you insert both these elements into the bag. So this is 8 2i plus 1 and 8 2i plus 2. First you insert both these elements into the bag. When you insert both these elements into the bag, this bag is of size I plus 2, right? So this bag becomes of size I plus 2. But you need a bag of size I plus 1. You need to remove one element. Which element should you remove? Remove the smallest element from this bag. Doing this ensures that no condition for the prefixes is broken. Because for all the prefix, we had an optimal bag. So the conditions were still valid. And for this entire prefix, you have to make a bag of length I plus 1. So the condition for this bag is also intact. Okay, so some of you are saying to dry run the second last test case. So let me do it once. So let me take 87419256. Okay, give me a minute. Okay, so let us start. So this is the test case which we will discuss, which is 87419256. Okay. So the test case has 8 elements, 8, 7, 4, 1, 9, 2, and 5, 6. Okay. And these are the indices which are important to us. This is I equal to 2, I equal to 4, I equal to 6, and I equal to 8. I have assumed one based indexing. Okay. So let's start with the first case I equal to 2. At every step, what we will do, we will add the first two elements in the bag and then remove the minimum element. Okay. So initially the bag is empty. We add the last two elements in the bag. of the bag in the bag. So we add 8 and 7 in the bag. Okay. And then we erase the last element, erase the minimum element. So we erase this minimum element. Fine. So the bag contains one element, which is 8. Okay, now let's do the next iteration. So let's do I equal to 4. If in I equal to 4, we again insert 2 more elements in the bag. Which 2 more elements? This 4 and 1. So now I have 8 and 4. Let's continue it for the next iteration for I equal to 6. So the idea is simple, add 2 more elements in the bag. So let me add 9 and 2 in the bag, 8, 4, 9 and 2, and remove which element? The minimum element. So let me remove 2. Fine. Now let's continue once for one more iteration. So this is I equal to 8. Again add 2 more elements in the bag. Which 2 elements? 5 and 6. So let me add 5 and 6. We have 8, 4, 9, 5 and 6. And now erase the minimum element from the bag. So finally what the bag contains those elements which Alice will pick. So which elements Alice will pick? Alice will pick this 8, this 9, this 5 and 6. So what is the score Alice will get? He will get 8 plus 9 plus 5 plus 6. What does this become? This becomes 28, I suppose. 6 plus 5, 11. Yeah. This becomes 28. Let me just check. Yeah. So it matches the answer 28. Okay, great. So this is a simple greedy solution, and the idea is that if you have an optimal bag for the first I-1 elements, you just take the 2 fresh elements and insert it into the bag, and then remove the last element from the minimum element from the bag. What will it ensure? This will ensure that okay, this will first of all removing this minimum element from the bag will not break the condition for any prefix, right? Because removing, suppose you have a bunch of elements where the condition is satisfied, if you remove one of them, the condition still remains satisfied. And since you are removing the minimum element, it will also ensure that Alice takes the largest value. Okay, great. So if this is clear, let us start with the next problem. So this is the last problem which we will discuss in today's PCD. It says asymmetric cookies. And the question says that Alice and Bob have n jars of cookies with them, and the ith jar has AI cookies. And they will take turns eating the cookies with Alice going first. However, they eat cookies in different ways. Okay, how do they eat cookies? On her turn, Alice will choose any jar that contains at least one cookie and eat one cookie from it. Okay, fine. On his turn, Bob will choose any jar that contains at least one cookie, and if the jar contains 3 cookies, he will eat 2 of them. Otherwise, he will eat only 1. Whoever eats the last cookie is considered the winner. Alice and Bob are both aiming to win and will play optimally to achieve this. So Alice has n possible first moves, each corresponding to choosing a different jar. How many of them are winning? That is, how many of Alice's first move results in a state where Bob has no winning strategy. Okay. So let me discuss this the question once. So the question says something like this. Basically, there are lots of jars. Okay, so there are multiple jars present which have some number of cookies in it. Fine. So there are some jars which contain 1 cookie. There are some jar which contains 2 cookies, and there are some jar which contains 3 cookies. Now there are 2 people, Alice and Bob, who would love to eat cookies from these jars. So Alice's strategy is simple. Nothing complicated. He picks any jar and eats 1 cookie from that jar. Nothing else. So he will pick any jar and will eat 1 cookie from that jar. Okay, so suppose Alice goes to this cookie, to this jar. It has two cookies. He eats one from it. So now only one cookie is left. Okay, but Bob has a slightly different strategy. Bob goes to any jar. So Bob goes to any jar. So suppose Bob goes to this jar. If he sees that okay, there is only one cookie left, he will eat that cookie, no problem. If Bob goes to a jar where there are two cookies left, he will again eat one cookie, no problem, and the number of cookies will become one. But if Bob goes to some jar where he sees that there are three cookies left, so Bob becomes greedy. He eats two cookies out of those three jars so that only one cookie is left. Fine. So this is how Alice and Bob eats the cookie. So the guy who does not gets to eat a cookie in his turn finally loses, and we need to and the guy. So basically, the guy who eats the last cookie wins the game. Now there are n jars, right? The question asks in how many of these jars. So suppose so the Alice has n first choices. Alice can pick, so there are n jars j1 to jn. Alice can pick some ji, so that would be his first choice. So there are n first choices Alice has. He can pick any of the jar out of that, right? So now the question is, in how many of these first choices Alice has a winning strategy? That means Alice can win the game. So out of these, the n first choices Alice have, in how many ways Bob cannot force to win the game and make Alice lose? So that is the question. Okay. So now let us analyze this problem a bit by bit. Okay. So one thing which is important is, what if there are no jars with three cookies? Okay, so what if there are no jars with three cookies? Fine. So what happens if there are no jars with three cookies? So in that case, remember that the strategy of Alice and Bob is very similar, right? If there are no jars with three cookies, then Alice picks one jar and eats one cookie from it. Similarly, Bob also picks any one jar and eats one cookie from it. The only difference arises in the strategy when there are jars with three cookies. Because in that case, Alice has a different way of eating the cookie and Bob has a different way of eating the cookie. So there, the problem will be different. But nevertheless, if there are no jars with three cookies, then the strategy for Alice and Bob is similar. They take one jar and eat one cookie out of it, right? So in this case, don't you think that the idea is very simple? Like if there are no jars with three cookies, then it only matters whether the total number of cookies is odd or even. If total number of cookies is odd, if total number of cookies is odd, who will win the game? If total number of cookies is odd, since Alice starts the game, the last guy to have a cookie would be Alice. So Alice will win the game, irrespective of how it starts and how what is his starting choice. Similarly, if the total number of cookies is even, so if the total number of cookies is even, then Bob will win the game. Right, nothing complicated, because at every step one cookie vanishes. So if there are no jars with three cookies, if the total number of cookies is odd, Alice wins, otherwise Bob wins. As simple as that. Okay, for the sake of simplicity, for the rest of the solution, let me say that x is number of jars with one cookie, and y is number of jars with three cookies. Okay, so this is a convention which I will follow for the rest of the solution. Okay, give me a second. Yeah, so let us continue. So what did we discuss? We discussed that if y equals 0, so there are no jars with 3 cookies. So there are two cases. First case is if x is odd. So if x is odd, then what is the answer? If x is odd, then whatever happens, Alice wins, right? If x is odd, then the total number of cookies is odd. That means whatever happens, who will win? Alice. So that means the answer is n. Because out of all the n starting choices which Alice have, he will win in all of them. Similarly, if x is even, then what is the answer? If x is even, then whatever starting choice Alice makes, he will lose in all of them. So that means the answer is 0. Fine. So this is important. Note that what basically happens, it is very important in this problem to understand how the parity of x changes. So how does parity of x changes? So think about Alice. So think about Alice and Bob. And what we are discussing is parity of x. So we are discussing about parity of x. Because parity of x is very important to analyze in this problem. How? So think about what happens when Alice eats a cookie with when Alice eats a jar with just one cookie. If Alice eats a jar with just one cookie, so the number of jars with one cookie basically reduces by 1. So that means its parity changes, right? So that means its parity changes. If Alice eats a jar with one cookie, the parity of x changes. Similarly, if Alice comes and eats a jar with 2 cookies, then that jar with 2 cookie becomes a jar of 1 cookie. So that means the value of x increases by 1. So in this case also, the parity changes. So what do I mean by when I say that the parity of x changes? It means that if x was odd initially, x becomes even, and if x was even initially, x becomes odd. Okay. So if Alice eats a cookie from a jar with one cookie, then the parity of x changes. When he eats it from a jar with 2 cookies, then also the parity of x changes. Okay. What happens if Alice eats from a jar which has 3 cookies? In this case, what happens? Basically, there was a jar with 3 cookies. Alice ate it from there. So now that jar has 2 cookies. So that means the value of x remains unchanged. So that means the parity of x does not change. Unchanged. Fine. Now what happens from Bob's perspective? For Bob's perspective, the first two cases are similar. Right? So for the first two cases, it is similar as Alice. But for the third case, but think about the third case. For the third case, if there is a jar with 3 cookies, then Bob eats from that jar and converts it to a jar with 1 cookie. So that means the value of x increases. So that means the parity changes here. Fine. So this is something very important to consider for the rest of the explanation, that whatever Bob does, so basically whatever Bob does, the parity of x changes. But Alice has a choice. Alice can always choose a jar with 3 cookies and force that the parity of x does not change. Okay. So if Alice chooses from a jar with 1 or 2 cookies, the parity will change. Otherwise, the parity will not change. Fine. Now, what should Alice want? So the basic strategy is, so in all these problems, we need to devise a winning strategy, right? So usually in all these problems, the winning strategy is based on the parity of some variable only. So here the winning strategy is based on the parity of x. Alice basically Alice should try to keep parity of x odd, parity of x even after his move. Why am I saying so? Because think about this. Suppose Alice has the move, okay, and Alice made the move, and after he made the move, he gave the game to Bob, and after Alice makes the move, he has made the parity of x even. Okay, so Alice comes and makes the parity of x even. So what will Bob do? Bob has no choice but to change the parity of x, right? We have discussed it in the last page that Bob always changes the parity of x. Whatever he does, the parity of x will definitely change. So that means if Alice comes and hands over the game to Bob when the parity of x is even, so Bob has no choice but to change the parity to odd and give it back to Bob. Right? So if Alice can always ensure that whenever he hands over the game to Bob, the parity of x is even, then whenever the game comes back to Alice, the parity of x is odd. But if the parity of x is odd, that means there is at least one cookie in any one of the jars. So he can always pick from that cookie and he will never lose. Okay, so what is the winning strategy of Alice? The winning strategy of Alice is to keep the parity of x even after his move. After his move, if he keeps the parity of x even, then that would ensure that Bob never loses the game. Because after his move, parity of x was even. Bob changes the parity of x, so the parity of x becomes odd. And if the parity of x is odd, then that means that there is at least one cookie in the jar, so Alice will not lose. Fine. So Alice has a winning strategy of keeping the parity of x even after his move. Okay, and that basically happens when y equal to 0. Now think about the first case which we have already discussed once again. What happens when y equal to 0? So we discussed two cases there, right? If y equal to 0, first case was if x is odd. If x is odd, what will happen? If x is odd, then Alice will come. And in the first step, Alice will try to change Alice will come and change the parity of x and make it even and hand over to Bob. Okay, so if he does so, he will always win. And that is the reason the answer is n. Similarly, if x is even, and since y is 0, that means Alice has, when he gives the game to Bob, the parity of x becomes odd. So he has no choice. So that is the reason here the answer is 0. Fine. Now, let us discuss the other cases. What if y equal to 1? So that means there is one cookie. So that means there is one jar which has 3 cookies. Right? Again, there are two cases. What if x is okay? So what if x is odd? Okay, let us just a second. Yeah, fine. So if y is 1 and if x is odd, so what is the strategy of Alice? When he will hand over the game to Bob, he will try to make x even, right? Because doing that ensures that Alice wins the game. Fine. So what he can do? So that means Alice, if x is odd Alice needs to change the parity of X before handing it to Bob. How can he do it? Remember what Alice did. What was, how did Alice change the parity? Basically, if he took one, if he touched one or two cookie jars, then the parity changes. If he takes a 3 cookie jar, then the parity remains unchanged. So here the parity changes, and here the parity remains unchanged, right? And what is Alice's strategy? The strategy of Alice is to Alice is to make the value of X even when he gives the game to Bob. Okay, so if X is odd, he needs to make it even. If he needs to make it even, he needs to change the parity. So he has to touch either of these two jars, either 1 jars or 2 jars. So how many winning choices? N minus 1 winning choice, right? He cannot choose this jar y equal to 1. That means there is one jar with 3 cookies. He cannot choose that jar because choosing that jar would keep the parity odd. So he will choose the other 2 jars, like all the other jars, and he can win the game. Similarly, if X is even, then the only way, if X is even, then the only way Alice can win is by not changing the parity. And for not changing the parity, he basically needs to, the only way to not change the parity is to choose a jar which has 3 cookies, and there is only one such option. So if any X is odd, we print n minus 1, otherwise we print 1. Okay. So this is the case for y equal to 1. Great. Now let us discuss the other cases. What happens if y equal to 2? So this is the case when y equal to 2. Okay, fine. If y equal to 2, again we have two cases. The first case is what happens if X is even. Okay. Yeah. So what happens if X is even? So now basically there are 2 jars which have 3 cookies each. So what happens if X is even? If X is even, now the idea of Alice is, okay, so before discussing this, there is one thing which I should discuss, and this is the following. We have already discussed that if there are no jar with at least 3 cookies, then the idea is simple, right? If X is odd, then Alice will win. If X is even, then Bob will win. That is simple. Now I need to prove one claim, and the claim is that if there is at least one jar, so if there is at least one jar, so if y is greater than equal to 1, so that means there is at least one jar. So that means the answer is at least 1. That means Alice can win somehow. Maybe not all positions can make Alice win, but Alice can win somehow. So that means we will not print 0. That is my point. If y is greater than equal to 1, so that means if there is at least one jar 3 bag, then Alice can win somehow. How? So suppose y is greater than equal to 1, and suppose X is odd. Okay. So if X is odd, what will he do? If X is odd, then Alice can simply, what he can do, he can choose a jar. He can choose a jar which has 1 or 2 cookies and give that to Alice and give that to Bob. So the parity will become even. When Bob gets it, the parity will become even. Bob has no choice to give it back when the like when the by flipping the parity, so x remains odd, right? So that means if x is odd, then Alice can always win. Similarly, if x is even, if x is even, then what can Alice do? Alice can choose this, like Alice can choose this jar which has three cookies. So doing that will not flip the parity, right? So x would remain again even. And now again Bob has no choice but to flip the parity and give it back to Bob. Again, give it back to Alice. So my point is that if there is at least one jar 3 bag, so if there is at least one jar which has three cookies, then Alice can tweak the game in somehow such that whatever be the parity of x, he can finally give an even x to Bob, so that he returns an odd x. So that means if the value of y is greater than equal to 1, then there is somehow Alice can win. So that means if there is some starting position where Alice can ensure that there are at least one, so that there is at least one jar which has three cookies, then Alice can always win. Right. So this actually solves a large bunch of cases. And the cases are like this. What if y is greater than equal to 3? Okay. If y is greater than equal to 3, then whatever be the first choice of Alice be, Alice makes any starting choice. Okay, Alice for any starting choice, then Bob makes a choice. First Alice makes a choice, then Bob makes a move. Now again the game comes to Alice, right? But when the game will come back to Alice, there, since the value of y was initially greater than equal to 3, here the value of y will be at least 1. And now here Alice can smartly play the game so that he can finally win. This we have already discussed. That if the value of y is greater than equal to 1, then there exists at least one starting position from which Alice can win. So that means if the value of y is greater than equal to 3, then Alice can start for any starting position. Then wait for Bob to make a move. And finally, when in the from the next move, Alice can start playing strategically and win the game. So that is the reason if y is greater than equal to 3, the answer is simply n. Right? If you look into the code, look what I have done. If the value of count 3, what is count 3? Okay, let me show you the code step by step. So I've taken the vector as input and I've counted. So count 3 is basically the value of y, count 1 is basically the value of x. Count 3 is basically the number of jars which have 3 cookies. Count 1 is the number of jars which have 1 cookie. Okay. And here, and parity is basically the parity of x. And if count 3 is greater than equal to 3, that means the value of y is greater than equal to 3, then the result is n. That means for any starting position, Alice can simply win the game. Fine. So this case which we have already discussed, if count 3 is greater than equal to 3, the answer is n. And this case also we have discussed. So suppose the count 3 is not 2, so count 3 is 0 or 1. So here we have discussed, if count 3 is 0, then parity 1 means answer is n, otherwise the answer is 0. And if count 3 is 1, then also parity is 1 means answer is n minus 1, else answer is 1. Okay. What remains is discussing the case y equal to 2. So now we discuss the case y equal to 2. So we discuss the case y equal to 2. Okay. So again there are two cases. The first case is what happens if x is odd. And as we see, what I've done, if x is odd, I've printed answer is n minus 2. Okay, why so? Think about it. Okay, first let us discuss the case when x is even. If x is even, Now we argue, as written in the code, that if x is even, then the value of answer is n. That means for all starting positions, Alice will win the game. Why? Think about it. So, if x is even, now x is even and y is 2. So suppose Alice comes and chooses, so Alice comes and chooses one jar with which has one or two cookie. So okay, so Alice in his first step, so these are the n minus 2 choices which Alice have. So he does not touches any jar which has 3 cookies. He touches a jar which has 1 or 2 cookie. Okay, if he does that, there are n minus 2 such choices. Then Bob makes a move. But when the game now comes to Alice, 2 jars with 3 cookies, right? But Alice has not touched any jar with 3 cookie. So that means after Bob's step, there is at least one jar remaining which has 3 cookies. And we have already discussed, if there is at least one jar remaining which has 3 cookies, then Alice can strategically play the game and win it. So that means these n minus 2 positions Alice will definitely win, irrespective of whether x is even or x is odd. Right? So these n minus 2 positions Alice will definitely win. So what remains is analyzing the remaining two positions where Alice touches a jar which has a 3 cookie. Okay. So suppose the parity of x is even. So now let us discuss this case. So suppose parity, so Alice touches a jar. Alice touches a jar which has 3 cookies. Okay. And we remember, if Alice touches a jar which has 3 cookies, then the parity of x does not change. Okay. So that means the parity of x, whatever parity of x initially was, Alice handed over the same parity of x to Bob. Okay. And here the value of x is 1. This is the same parity. And now the value of y has, here the value of y is 2. Here the value of y has become 1 because Alice has touched the jar which has 3 cookies. Now note that in this step, Bob has to touch the jar which has 3 cookies. Otherwise he will lose. If Bob does not touch a jar which has 3 cookies, then again the game will come to Alice. Alice will get at least one cookie, at least one jar which has 3 cookies, and he can definitely win from there. So that means Bob needs to touch a jar which has 3 cookie. But if Bob touches a jar which has 3 cookie, then that means he will flip the parity. Right? So the parity gets flipped. That means what happens if x is even? If x is even, then it goes to the same parity as Bob and he flips, and finally the parity of x becomes odd. Okay, so that means if x is even, then Alice finally gets it with an odd parity, so that means he wins in these two positions. And if x is odd, then he loses in these two positions. Okay, so in these two positions he loses, and the remaining n minus 2 positions, they were definitely winning irrespective of in the remaining n minus 2 positions they were winning irrespective of whether what move Bob makes. So if we look into it, that is what we have done. If the parity is even, we have printed the result as n. Otherwise, we have printed the answer as n minus 2. Okay, so that was it for the solution of this problem. Any doubts? Okay, great. So that was all for today's PCD. Thank you, everyone.